to introduce our keynote speaker. So Laurie Marks is an emeritus professor here. As you can see from his bio and his presentation, he has done a lot of work on electron diffraction and structural science. I think he has worked with electrons most of his research life here. He has worked both theoretical and experimental processes in this science. So he will be hopefully presenting today both some flavor of theory and experiment. So especially on the aspect of using direct methods that most of us are familiar with and how to use them for electron diffraction. So specifically for electron work, he has served the International Union of Crystallography and the American Crystallographic Association for a few years, as he acted as chair for the IUCR committee. And he has received numerous awards from not only from these societies, but from other materials-related societies related to structural work on electron diffraction and surface analysis. Okay, without further ado.
Thank you, Chris. I'm not sure I really deserve that. Okay, so I'm glad to be here, coming back post-COVID. It's one of the first times I've been back here since COVID. I find myself in a slightly embarrassing situation because I think I was doing electron crystallography, solving structures before some of you were actually born. So you will see that there's a slight historical element in some of what I'm going to be talking about. I will try not to go too deeply into the dynamical diffraction and nitty-gritty. How many of you suffered through my classes on electron diffraction, electron microscopy here? None, only one. Yes. So you can ask me many questions later. There's a big history that I'm going to show a little bit about. But I really need to start at the most important thing, which is acknowledging the students and the postdocs who did all the work. Like all professors, I actually just stand around and pretend that I did everything. But in fact, they are the ones who did it really over a long period of time, starting off with surface work for metal semiconductors back in the early 90s, to oxides, surfaces, strontium titanate, and a lot of other different oxides, surfaces. And then that migrated towards bulk. And I actually had a student who built the first precession electron precession diffraction camera at Northwestern University. He was in fact an undergraduate. It's not bad. He got a Hertz Foundation Fellowship, which is the top, as you may know. So let me start with moving this out of the way, if I can. Okay. There is an amazing contradiction, and you have to recognize this right at the start of anything to do with electron diffraction and understanding it. So we have 1927-28. There's Davison Germer and Thomson-Reed both discovered, essentially independently, electron diffraction. Let's not worry about the fact that Reed was only a graduate student and he died in a motorbike accident not too long afterwards, so he didn't get a part of the Nobel Prize. If any of you do really good work, graduate students, don't die. You'll lose all credit. They explained in their first work using kinematical theory, Bragg's law, and actually, to my knowledge, this is the first structure analysis using electron diffraction. Sorry, it's not 20 years ago. It's almost 100 years ago, 1933. And they refined the positions of hydrogen atoms in the solid. Quite an amazing piece of work. However, there was actually a problem. The first papers explained the diffraction from Davison Germer and Thomson-Reed using Bragg's law. But the second or third paper said, uh-oh, it doesn't actually work. And in 1928, Hans Bethe showed that in order to explain the positions of the diffraction spots properly, you actually had to use a full dynamical. And this is actually his experiment, some of the experimental data. That is where the position of the diffraction spot would be based upon Dragg's law. And you can see there's a significant deviation from the experimental results. First papers, this was ignored. Second and third, it was not ignored. And this has got to do with dynamical diffraction. Kinematical diffraction, you just think about the electrons from this direction going out to some diffraction spots. This is a different variation of electron diffraction, which is not being used so much at the moment for any of this work in crystallography, but probably could be. It's actually very popular in a different area in electron microscopy, electron crystallography. So you'd have this going out to here, to here, to here. That is kinematical. Quantum mechanically, it's first order perturbation theory or Born approximation. And it's not right. What you have to do is include the other terms. So this gets scattered back, this can get scattered over to there. Because of this 10 to the 5 factor of more intensity, more probability of scattering with electrons compared to X-rays, the dynamical diffraction is strong. And a classic example is a true kinematical sample would be about 30 angstroms of solid hydrogen. I'm actually quoting John Cowley. How many of you are working with 30 angstroms of solid hydrogen? None. Okay. So graphene, kinematical. A gold atom, a single gold atom, scatters the electrons about 20 times. So the positions may be different. The intensities do not necessarily scale with the structure factors, and they vary with thickness. Interesting point, lighter atoms often dominate. This is something that's very different from X-ray diffraction. And you actually have to understand and use a non-relativistic form of Schröedinger equation. Any of you who do quantum mechanics, thankfully we don't have to worry about exchange correlation with the electrons. We just have to do a Schröedinger equation. But this is a solved problem. John Cowley, who wrote an excellent book on diffraction physics, and I'll strongly recommend this to everybody to read, has this really nice quote. He actually did some of the original crystallography work. Thus, it was founded a belief, almost an article of faith, that it was impossible to interpret the intensities of electron diffraction patterns to gain information. This is true. And then you have this question. How did, in 1938, the positions of hydrogen atoms get refined? Then there's the work that John Cowley did. He refined, I think, boron hydride. Weinstein, Russian work. Nobody in the West paid any attention because, of course, it was in Russia. But they solved a lot of samples from powder diffraction averaged. And note that I use the word average. It matters. There's Takanyagi. I'll show his data later. Doug Dorset, Jonas, Wharton Sinclair. Incidentally, it's rather interesting. Wharton Sinclair was also involved in the first precession camera built at Northwestern, but he didn't publish that much. And the reason he didn't publish that much is Honeywell wouldn't allow him to, because he was using precession electron diffraction data for patents on zeolites. So there's a lot of hidden literature. So the key point, and you can leave now if you want to, all right? The crystallographic methods for solving structures, and I mean primarily direct methods, do not actually require the kinematical theory to be right. It's kind of a subtle thing. And so long as strong structure factors in general give you strong intensities, they are actually going to work. And the last one, which is well documented from calculations, but nobody has been able to explain, and I can actually tell you that some of the best theoretical people in electron microscopy have tried hard to explain it, is that averaging reduces the dynamical contributions. One of the key points is this. This is a little bit like a little structure of molecules. And when we are doing a refinement, direct methods or any other, we are essentially fitting something like an atom to these positions in a least squares fit. A very important thing to recognize is you do not actually have to have a sphere there. You can do it equally well with a cat. If you find the most probable position of the cat to fit this, it will actually be right within a little bit. And that little bit is your error. So, stepping back a little bit, how do you solve a structure? Well, guess and refine. Hopefully here nobody is doing this. Sometimes you have to. Use the Patterson function. Actually, a lot of the direct methods do that, although it's not so common with electron diffraction beta. DFT can work, cannot work. I'm actually involved in one of the major DFT codes, so I know just how bad it can be, and good. Get an image. Well, we're not talking about this here, but this is also very important. And get a diffraction pattern. When you come to a diffraction pattern, there's a few fundamental points that are important. And this is very nicely put together in a paper by Patrick Combetz some years ago. Incidentally, I will make available a list of all the references that I have here, and I'll also make sure that Chris has got a copy of my PowerPoint. Like all professors, I was furiously changing it this morning. Right. So you need some model. You need a priori information. Incidentally, if you really know anything about direct methods, this is where everything is, the presence of atoms. You need a way to fit it, and you need some math. One of the key things is the phase problem. And maybe you've all seen this one before, but it's really important, so I'm going to show it to you anyway. You have a wave function. We use wave functions when we're talking about electron diffraction. And in real space, there's an amplitude. In reciprocal space, a different amplitude Fourier transform relationship. You would measure an intensity in either real or reciprocal. And in both of these two, the phase term has vanished. Does this actually matter? So let me give an example. Suppose that I take the phase, an apple and an orange, and I take the phase of the orange and the amplitude of the, sorry, other way around. It's the phase of the apple and the amplitude of the orange. And I put the two together. So what am I going to get? Are angular? Yes, apple. And this is actually a very important point, because you do not actually need the intensities to be strictly kinematical if the phases are correct or adequately correct. And in fact, you can tolerate a certain amount of phase error. This is an example of a test molecule phase error going up to 40 degrees, really large. This there, bit messy, modulus correct. Here, modulus error, and go all the way up, and in fact, it is pretty much there. So long as you have an adequate representation of the intensities and a better representation of the phases, then you can actually recover a structure from data, whether it's X-rays, neutrons, electrons, whatever. And what we are doing here, I have in a little caricature, indirect methods is putting the tail on a donkey with your eyes closed. Fundamentally, in direct methods, we have our eyes open. And we are using the fact that we know that there are atoms, we know the wavelength of the electrons, we know the wavelength of the X-rays, we know the structure factors, we know a lot of other things as well. We may even know what the temperature is. And from the temperature, you have an idea about the Debye-Waller terms. And the strategy that is always being followed is to go from an infinite number of possibilities, which no graduate student worth anything should ever want to attempt to do, down to a finite number, and then you do R factor, a chi-squared, and incidentally, I would urge people to think seriously about chi-squared for electron data. There are good statistical reasons why people don't use chi-squared that much for X-ray data, and it's got to do with the irreproducibility of measurements from synchrotrons. If you've ever looked at the raw data, it can be pretty horrible. All right. And then, of course, you've got DFT and chemistry, bond valence sums, sanity checks. A nice little point here, and this actually comes from Chris Gilmore, who was one of the people who pioneered the maximum entropy method, which at one time was thought to be the most important. If the moon's in the right quarter, you actually get a real space potential or a charge density. In other words, what was suggested in the first slide about getting back everything. In other cases, the atom positions may be wrong by 0.1 to 0.2 angstroms. The peak positions may actually be wrong. There may be too few or too many. But that is enough to solve the structure, assuming you actually know how many atoms there are there, and ideally what they are. If you don't know how many atoms and you don't know what they are, life gets to be really tricky, which is why I was very glad to see that there's now an EDX system added to these instruments. And what we are doing is, given the data, we are not going directly back to the structure. You may think that is what you're doing in your experiment, and in fact, the computer is spitting out some sort of result, but it's actually not doing that. You are using some methodology, and nowadays, charge flipping is the most common, and there's good technical reasons for that, because it is more resistant to some of the effects of dynamical diffraction, and you're getting a trial structure, and then from the trial structure, you get back to the full structure. Just bear this in mind. I'll mention later, this part here has actually not received a detailed analysis for electron diffraction by anyone, to my knowledge. It's a big hole. So, when does electron diffraction work? So the first case is kinematical theory, or kinematical cases. Surfaces is one of the most common cases because a surface is really one monolayer, and there are experimental methods of differentiating the scattering from the surface from that of the bulk. This will also work for something like graphene, and you may know that the structure of nanotubes was solved by Sumi Uejima from diffraction patterns. Actually, because it's a helix, so it actually resembled the DNA. 1985, this is actually a classic paper, one of the most highly regarded, except I've not heard almost anybody in the electron crystallography literature reference it. 1985, people had tried by STM, by X-ray, by low energy electron diffraction, by everything under the sun, and failed. Takuniyagi managed to solve the structure. This is his diffraction pattern, not very well represented. That is the Patterson. He actually just used the Patterson and solved it. It's actually a very complicated structure. I think it's got about 15 unique atoms in the unit cell. You know, not one or two like hydrogen positions in ammonium chloride. Very complicated. And incidentally, I haven't lost it here, but the R factor he had for this refinement was about 0.35. But he solved it, and he was right. And one of the interesting things is, even though there are some dynamical diffraction anomalies, this is actually data that we recorded a few years later, most of this, you'll see, has got six-fold symmetry. This structure has, in 2 dimensions, got P6mm symmetry. So it should be six-fold. You'll see there's not quite six-fold over here. And I put this one in at the last moment because I asked the question about errors. This is experimental errors that we measured from repeat measurements. In other words, you take a whole set of measurements from the same and then look at the statistical deviations. And interestingly, it's fixed, which is quite different from what you're actually doing with an R factor fit. In an R factor fit, you're actually assuming some sort of signal to noise ratio. Depends upon the signal. Slightly different case. Now, I don't know how well you can see. Yeah, you can see it. Those spots here are the ones which were measured by a student, Arun, looking rather pensive back there. Then it was later on solved by Geomentikin, who was actually a shared student with Ken Poppelmeyer. This is the direct methods restoration. There's a lot of details about this, which I won't go into now, but it's almost similar to charge flipping. Those obviously would correlate to strong peaks. And then if you do the analysis in more detail, the structure fitting, this is what you come out with. Complicated system. You've got titanium atoms and oxygen atoms arranged in a network structure. You may notice something similar to zeolites, but this is actually in a two-dimensional case on the surface. And you can go and represent it in terms of tetrahedral models. And this is 2010. This is some time ago. There are earlier work that we did on semiconductors. Second case, 1s channeling. Now, this is a little bit technical. I'll give you a little explanation without going too far into the details, but it's now well established. There's a paper here where we looked at some of the different methods. So the concept is that in most cases, when you have electrons coming down, you can think about what's going on as having a deep potential and nothing in between. The electrostatic potential for electron diffraction is mainly at the nucleus. So it's really rather small. It's actually something between half an angstrom to maybe 3/4 of an angstrom away from the actual position. Outside of that, it's really pretty small. So this is a decent approximation to call that 0 and say you just have the atoms. So if it's 0 here, you can separate what's going on in this column and do what's called a string potential, where you average down this potential and then solve in a particular form of Schrödinger's equation. This is, if you know your quantum mechanics, this is something called the WKB approximation. And then what you will find is the electrons channel down like this. And you get something which is really rather important, excuse me. And to illustrate this, I'm going to take 1 minus the wave function, the modulus of this, and look at what is going on in real space with full dynamical diffraction. And what I've got here is perchloro copper phthalocyanide. So those are your bromine, here are your aromatics chains, and there is copper. And hopefully you're going to be able to see this. You probably can't see, because somebody turned the light off in the front. That's better, maybe. You may be able to see that the carbon is almost invisible. That's a very, very thin case, dominated by the bromine. Now go to 4 nanometers. Now you can see the carbon. And the bromine actually is not any stronger than it was before. It, in fact, oscillates. There's the copper. If I go thicker, in fact, the carbons are even stronger. And if I keep on going in thickness, you'll find the carbons and the nitrogen, in fact, start to dominate. And you get interesting, these are actually 2s type states. You get states which are rather like atomic states. So 1s, 2s, etc. And I could keep on going. And you'll see that as you get thicker, you get intensity at the atom positions, but it stays there. And if you, excuse me, If you know anything about direct methods, then you know that having charge and regions in between with almost nothing in it is one of the key things that helps direct methods to work. Yeah, my apologies, I'm sort of not used to talking this much. There is an important relationship from this. And this is some work that was done by a couple of postdocs, Felix Tchaikovsky here, who is an X-ray dynamical diffraction expert who wrote moderately incomprehensible papers on dynamical X-ray diffraction, which unfortunately at that sometime around then I was an Actor-Christ A co-editor, and he kept on sending to me to review. Right, and another postdoc who actually went off to Air Force and made a very good career. What they worked out is that there are certain kinematical relationships. So that is the Friedel's law. In dynamical theory, it turns out that it's only approximately correct, but it is statistically approximately correct. In other words, the average value for G and minus G phases. Thank you. Yes. The average value of the plus and minus phases are actually the same, complex conjugates. Similarly, there's something called the sigma 2 relationship. It's called the triplets. That is also statistically correct. And this is the results of the calculation. This is sort of a scatter plot of cases, and you can see that there is a preponderance that as you go up to higher intensity, higher amplitudes up here, it gets smaller, and this looks like the standard Cochrane distribution. And that is for the phases and also for the triplet relationships, which is statistical. And this is sort of one of the key points. And because of this, this is Wharton Sinclair, this is some work done jointly with Ken Poppelmeier. We're actually able to solve an unknown transparent conducting oxide. This is 1998. I think this was our first bulk structure solved. And it was confirmed later by neutron. The paper, some of the people don't actually realize, who've looked at this later, that we in fact gave the sample to the people to do neutron diffraction after we'd solved it. Moving on. There is something important called intensity ordering. And I said right at the beginning, if the structure factor kinematically is strong, we want the experimental data to be strong as well. It doesn't have to be proportional, it just wants to be strong. Nice quote from Doug Dorset, it's the first one. He used to say this: if the experimental pattern is similar to the Bragg's law one, then the structure is solvable. And I rephrase it in a slightly different way. I would say if the deviations from the Bragg's law or kinematical are small, in other words, random noise, then you can solve it. In other words, if we've got data here, then it's close enough to a straight line that we can solve. If everything was down here, we'd be in trouble. And in fact, this has been known to be the case since 1937, but people didn't notice it, or people didn't put the dots, combine the data to explain. So this is work by Blackman, experimental work, and he compared the kinematical structure factors and something which is called a two-beam model and analyzed it, and you find that essentially it follows a nice curve. There's a region here where they're very close, and even here, if the structure factor is large, the intensity gets to be large. There are some regions which are very different. This is something called systematic row conditions. So it's not always true. You still have to be careful. And then in the last type of issue or case is average data. And this one is really subtle. It's understood in the sense that quite a few people, my group, Paul Midgley in Cambridge, Jean-Paul Morinoli in Lille, if I remember correctly, all have looked at this. None of us can explain it, but it's there definitely in the calculations. So this is precession, which is where this whole was put together. This whole thing came from. In precession electron diffraction, what you're doing is, instead of taking a single diffraction pattern on the zone axis, and this is what you would get. Incidentally, this is calculated electron diffraction data, and the size here is proportional to the intensity. You tilt off. So you bring a tilt this way, bring it over, and then bring it back so that it's going to stay at the same position, but you've now tilted, and there would actually be the Ewald sphere. And as was mentioned earlier, you have less dynamical effects, not none, but just a little bit less. And then in precession electron diffraction, what you do is rotate it. Come on. Not quite this slow, of course. And then you average. So the data that you create experimentally is an average over essentially electron beams going around in a cone like that. As an example of what this does, this is the case for andalusite. This is actually both experimental and calculated data. And the same method of preparation as people are using now with the Rigaku instrument, which is you crush and disperse. And if you want to ask me, how do you make the sample and is it painful? The answer is it's easy to make the sample and it's painful to find the good crystals. Always has been. This method has been around for, I think, before I was born. Yes, certainly before I was born. Okay, so this is the Bragg's law, in other words, sort of kinematical. And you may notice that there's no spot here. That is a forbidden spot. In electron diffraction, in many cases, forbidden spots are allowed. And this is because that can be due to dynamical diffraction. There's ways to get to that location there. For example, from the origin, you can go up to here, and then you can scatter by that, which will take you to that forbidden spot. And associated with screw axes and glide planes. That is the calculated, if I remember, in red, and the experimental in black. So not bad. Now what I'm going to do is go to cases with precession for different angles. So as we change the angle, we're averaging more. So that is 6.5 milliradians, which is fairly small. And all of a sudden, you can start to see, actually, let me go back 1 second. Let me point out one thing. You notice that spot there, which would go here? It is actually the strongest spot in the diffraction pattern, and it is forbidden kinematically. This is actually not something that is an anomaly. This can actually occur. Now, 6.5 milliradians, you'll see that's starting to drop in intensity. 13, even more. 18, yet more. I think there's one more. By the time we go up to 24, let me see. Yeah, 32 is essentially vanished. So forbidden spots, the things that you use in a lot of crystallography to determine the space group, those are obeyed better if you average than they are from a single diffraction pattern. And it actually decays something like exponentially. And as I mentioned, we actually worked this out in the same time Jean-Paul Morinoli and Paul Midgley were publishing on the same result. There's cases I showed you a long time ago, well, 10 minutes ago, right? The Blackman curve, and I said there are some anomalies. Those actually are cases where it does not follow this. But there's reasons why that's the case. It's in the theory. It's something called a systematic row condition. And if you want, you can ask me over lunch, as long as you give me something nice to drink or something. The other thing is a little bit more subtle, and this is related to the averaging and how quickly does the averaging work. And again, this is something where we worked on it. Morton Sinclair mainly did this, but also Paul Midgley and Andy Stewart in England were doing essentially the same type of analysis. We couldn't explain it, but it's just calculation results. So you start off with one calculation here, try a few at different angles, and then you start to doing some more, and you average them, and you sum, not exactly the same way you do experimentally, but you sum in a computer to see what is going on. And what you find if you do a single calculation, the deviation between kinematical and experimental gets to essentially unity. In other words, it becomes horrible at any reasonable thickness. If you've got 3 settings, all of a sudden it gets better. Average over 5, average over 21. In other words, more that you average, the more pseudo-kinematical the data becomes. I actually don't like the term effectively kinematical or truly kinematical or anything like that. I do like to call it pseudo-kinematical. And I would recommend that you use that term. And the final step, I'll give time for plenty of questions. Refinement. Actually, refinement using dynamical diffraction has been done for a very, very long time. This is just one of our papers, 1993. We did it a little bit earlier, and there are some cases, I think, going back 10 or 15 years before that. So this is on the 2x1 surface. What you do is you take a sample with positions, you have a bulk, you calculate the diffraction from the top, you calculate the diffraction from the bottom, you move the positions. It is terribly laborious, but it works, and computers are getting faster and faster. Of course, when you use dynamical diffraction data, the agreement between experiment and calculation is really very good. The main limitations for this are actually, what is the sample? What really is the orientation? How thick is it? If you've done a lot of electron microscopy, you may know those are really rather nasty questions. You never actually know how thick your sample is. You just make a good guess about it. So there's a very good correlation between experimental data for the kinematical and the multi-slice. Some more recent data from Lucas Palatinas, very nice guy in Czechoslovakia. There's here a refinement on the left of mordanite. You may note that the map here with dynamical refinement is very much cleaner than the map here with kinematical. Both have still got peaks at the atom positions, but with dynamical interpretation, it's much cleaner, which is what you would expect. And in fact, the positions are good and the R factor can go down to 0.093. I asked him for the reference and he sent me this, and he said, as an aside this morning, oh yeah, that's actually rather a high number. Nowadays, it's about 0.06 that we expect. And this is one of my older works, 2009, refining charge density. I should comment that hydrogen positions, maybe you can refine them with electron diffraction data, maybe you can't. It can actually be just as bad as with X-ray data. They can be unstable. Most of the programs probably constrain the hydrogen positions. If any of you use ShellX, it's got all sorts of constraints that make things work. So here, this is actually a density functional theory calculation. The red is the bonding density. These are two different fits. This one is not so good. This one is rather better. And that is the bonding density experimentally measured. And there's actually a little bit of dangling bond outside and various other features. And it's actually a pretty good match. And this is from one of Lucas's. more recent works from a ruthenium aluminum oxide, where he's actually refining the charge density and picking up rather nicely the aluminums as well as the lucretiums. Lucretiums, I think it's lucretium. Yeah. Yeah, I worked on rare earths for a bit, but only at the other end, gadolinium, dysprosium. And this is quartz, where he's refining the bond density. In fact, there's a very famous paper, slightly controversial, about 1990 by John Spence, observing the bonding in copper oxide, but from different data. So conclusions. Electron diffraction is often pseudo-kinematical. I don't like to call it kinematical, and I don't like to call it effectively kinematical. But if it's pseudo-kinematical, that is enough. Averaging over orientation helps. And this is actually another piece of work, I didn't go into any detail, by Wharton Sinclair. Actually, averaging over thickness helps. So we had earlier the case of your platelets. In fact, if all your platelets were the same thickness, the data would not be so good as if you had some variations in thickness, because the variations in thickness help. And also, interestingly enough, disorder. There's a little bit of rotational disorder in the material. It actually helps because disordered scattering is quasi-kinematical as well. That's a very subtle point, but it's used a lot to understand true disorder in material. Direct methods works despite dynamical effects. They are there. You can get the structure. The refinement may be okay, may also be a little bit off. Be careful, it may go unstable. But dynamical refinement is better. It is around. I guess that in Rigaku you have some variation of it. I think you could ask Lucas for his code. And I know somebody else who is putting together a dynamical refinement code for bulk. I do have a dynamical refinement code somewhere. It's ancient, and it probably doesn't work any longer. Who knows? Known unknowns. I really like that term. No adequate analysis has yet been done on the 3D averaging. I asked Lucas about this. He said, no, nobody's done a paper on it. It's a good project. So if anybody wants to put a year, do some experiments, it's not a bad idea. All right. Big one, in my opinion, structure completion. Everybody wants it to work, and you assume it works, and the basis for it working with kinematical data is very firmly founded. However, there's no reason it necessarily should work with dynamical data. And to my knowledge, that has never been explored, except I can tell you that I know of cases where it didn't work for me when I tried it. Positivity charge flipping is the method that works because it just requires that you have features and space in between, which is essentially what I was showing you with the channeling model much earlier. It doesn't rely upon the statistics. I think this is why charge flipping has taken over, at least for electron diffraction data, but I understand, in fact, in many other cases for X-ray data as well. And as one known unknown, or this is a known, acceptance by the US TEM community is weak, and there's a very good reason for this. And the reason is to do with various people who oversold it. And they said, no, there's no such thing as dynamical diffraction. Everything is kinematical. They did not look deeper and say, okay, it is dynamical, but maybe it mocks kinematical, pseudo-kinematical. Caveats. You'll always have dynamical diffraction. If you do a lot of electron microscopy, you know there are things called aberration correctors. The only possible dynamical diffraction corrector is an expert in dynamical diffraction theory. And there are not many of us left active. We're all slowly retiring. It is definitely known that if the sample is thick, it is not going to work. So you do have to have thin enough, which is why crushing is actually really rather good. A subtle point, and I did check with a few people, to my knowledge, people have not been doing all the standard IUCR crystallographic checking of everything. There may well be one or two structures which are wrong. Actually, there's one or two structures which are wrong with X-ray diffraction. Actually, more than one or two, as we all know. Right? Beware radiation damage. There are some materials, particularly fluorides, which are almost impossible to do anything with in electron microscope because the fluorine bond drops off. Aromatics are great, but non-aromatics, aliphatics, can be pretty horrible. Final thoughts. I really like this first quote from Albert Jean Yogi. Research is to see what everybody else has seen and to think what nobody else has thought. So bear that in mind when you think about electron diffraction and electron crystallography, and actually crystallography, because the last two things, little factoids, they're both true. So Lau, Frederick, Knickling, they discovered X-ray diffraction by not obeying their boss. Now, Max von Laue is one of my heroes. You may or may not know, he's, I think, one of the few major scientists who opposed the Nazi regime and stayed in Germany and lived. Did a lot of other work, right? And also, Germer and Davison, they discovered surface electron diffraction by mistake, by accident. It was not done deliberately. And on which note, we have time for some questions. These could be now. If you're going to the dinner, the reception this evening, I don't know how many people are going, you can ask me there, or you can easily find my email on Northwestern, or you can get it from Chris or so on, and ask me. I don't bite normally. Thank you.
One of the other ideas in applying direct methods is coming from small compounds.
A good point. I have no idea, but I would agree that it's good. No, I haven't gone that big. I mean, the silicon 7x7, which is about, well, no, I think the biggest we did was about 25 unique. And that, of course, way smaller than, but yeah, no, it's quite possible.
Don't get that.
Yeah. But in fact, it's one of the interesting things is that particularly with precession, that the electron data goes out to much higher. So the silicon 7x7 data I showed you, just for a single monolayer surface, had half an angstrom resolution. So it does go out a long way. And that was actually single beam. It was not precession. Precession, you can't go out much more than half an angstrom because it just doesn't scatter that much.
It's a bit of an ignorant question. Well, how much do we know about kind of, when it comes especially to organic species, predicting stability? You just mentioned the last slide, like aromatic hydrocarbons versus it sounds like CF bonds are extremely mild. How do we even predict that?
It's all known. You have to go and look in the literature, mainly the cryo-EM literature, where they've studied this a lot. Yeah. So aromatics are much more stable. The copper perbromothallocyanide, right? That is both aromatic, and the bromines pull away electron density, and that stabilizes. Then there are other interesting things like non-maximum valent materials are less stable. So TiO is more stable than TiO2. And that's another mechanism which, if you've, it's related to an Auger excitation. But there's a lot of work on all of this stuff. But you have to go and, you know, not look in the crystallography literature.
That having some disorder actually can give us some better data.
It makes it more kinematical, yes. Yes.
So some of these experiments actually, like, well, I guess you do a lot of them at room temperature, but slightly elevated, that can be thermal motion that would actually possibly lead to.
No, I don't think the thermal motion will actually help you. I mean, sort of just misorientation. So if you have a slight mosaic, it actually can help you a little bit because it's giving you a little bit of an averaging itself. All right. The work by Weinstein and his group in Russia, that was all powder diffraction. You know, and they were implicitly averaging over different orientations and even a little bit thickness. And it's not sort of until much, much later that people start to understand why that helped. Similarly, Doug Doucet was doing averaging because he had powder data. More questions, please. You'll be examined on this later.
Lunch should be outside, and at the end of the last session, then we all walk to the tech building.
Or at least use one.
So I have a
So I have an all organic material.
Mhm.
You said I need a thin material, but I could use thicker one and it wouldn't make as much difference for the dynamic.
Well, it depends how thick it is.
Okay.
I mean,
In
1,000,
other words, I can get too thick.
you can
and
get
still
to.
have trouble.
Oh, yes, yes, yes.
Because I mean, you know, the biggest effect that we saw was from the intensities of the heavy atoms.
Yeah, well, 100, yeah. Yes. So then for that, with the intensities from these heavy atoms will drop above about 30, 50 nanometers.
Okay. Yeah, but.
So if you're up to
but-
10,000
but-
nanometers, you're really, well, then you're doing X-ray, yeah.
Right, X-ray, right.
Yeah.
Right.
But sort of 1,000 nanometers is probably the real upper limit.
Upper
Yeah,
limit,
yeah.
okay.
But I don't know if any, again, we did work on things like the indium gallium oxide. And there, I think when you got up to about 60 to 80 nanometers, that was problematic.
Problematic, right.
Yeah.
But you're talking about the heavier atoms, which actually appear to have better, more
Yeah.
dynamic effects.
Yes, but they're still there, but they may not show so much in the
Final refinements.
yes. That's where there's a big difference between kinematical and dynamical. So the map may find them.
Right.